Well, in this lecture, we will talk about fault diagnostics and prognostics. By now, we have an idea on the three different types of maintenance, being periodic maintenance or preventive maintenance. Then we have the predictive maintenance, or what is known as condition based maintenance, and then we have the reactive maintenance. And in the class prior to this, we saw how FEMICA could be used to identify the critical equipment or machinery or operation, so that our maintenance efforts needs to be strengthened and we need to put more maintenance efforts. Now, in this lecture, I will be introducing you to certain definitions of fault diagnosis, okay? Because as you would have seen, I have found out by FEMICA a critical machine. Well, the next question is, so what? Well, obvious question comes to everybody's mind is, I have done maintenance. I am, of course, always monitoring its condition through an online condition monitoring technique. But people always ask, how can I find out if a fault has occurred? What kind of fault has occurred? Which component in the machine has failed? And if it has failed, or if it is deteriorating, how long is it going to last till the machine totally fails? Because you will see with time there is always a cost. Okay. If the machine is being maintained with time, because the wear and tear increases, the cost of repair perhaps okay. But time would come when I will reach a point where this is not economically viable to repair this. Okay. So, this point I can say it's time to replace the machine. Okay. I will just give you an example. There have been instances where gold mines in our country, people have not gone ahead and mined gold out of that mine, because the mine depth has increased to certain level, such a level that it is not economic to mine gold from so much underground. Okay. And then people think, well, it is not economically viable. So, end of the day, why are we maintaining this? If you recall, in the very first or second lecture, I had told about profitability. So, if I manufacture a good and if I do not make profit out of it, I will run out of business. So, to ensure that I manufacture quality goods, I have to have my machinery running at their desired specifications. I have to produce components at their as per within the tolerance limits of the designers and so on. But all these things will get affected if my machine which are manufacturing them are not perfectly maintained and so on. So, there are certain terms associated with this fault diagnosis, and then obviously people always ask at any given point of time. For example, if I have found a defect at this location in time and at this time, if I decide that this is my end of the life, people would be wondering what is this RUL of the machine, that is known as the remaining useful life of this machine. Okay. So, but then we will see how this is done. So, before I go into, I will give you certain elements of the CBM, okay, because we will in this class focus on condition based maintenance. Okay. And then which is also known as predictive maintenance. Okay. And then, so for doing predictive maintenance, I need to put in a sensor, some sensor, and then I will have this data varying with time, some data. I will do a feature extraction, or I will do this signal analysis and try to understand the machine's present condition. By present condition, I will say whether there is a fault or there is no fault. So, this is what with time our machine evolves. Okay. But if this operation is done, say for example, I am with time, I am monitoring a particular feature. By feature means a particular feature of this signal. For example, we will understand a mean value of the signal, or RMS value of the signal. It's nothing but root mean square value of the signal. Now, if I just plot this is at some time t 1, another time t 2, these are the values, and suddenly I see that with time this is increasing. Obviously, a higher value of this value means the machine is having a defect. These are all different t's. And so on. Well, who is doing this? This is at any given instance. In time, my machine is running. I put a sensor, get a signal, find out its RMS value at time equal to t 1. Next, I do the same thing at time equal to t 2, t 3, and so on. So, what happens? This frequency is up to you. It could be days, it could be weeks, it could be months. So, this is known as the trending, and you see it has come to a point that my machine would have failed if the level, this is my failure level. So, once it reaches this, it is a failure level. So, you see, for a simple system, if I can draw the equation for this straight line y is equal to m x plus c, where c is this intercept here and y becomes this level here, and m is the slope of this line, okay, and x is time. So, at any given time, if this equation to the straight line is known, I can find out at what x, or in this case what time t it is going to reach this level. So, at any given instant, if this equation is known to me, I can find out at this instance what is the RUL. Okay. So, in CBM or the prognostics health management cycle, if one needs to put sensors, needs to collect the data, do some pre-processing and extract the feature, classify the fault, whether they are what kind of classes they belong to, whether they are multiple, severe and so on, and prediction of fault evolution. See, through this example, I gave you a very small simple example of one parameter which is going linearly with time, and then I can find out what is the RUL. Okay. But it is not so simple in real world, and then you will see in the next lecture how certain machine learning techniques are being used to find out the remaining useful life of a plant, because end of the day I have diagnosed this fault, okay. I have found out the reasons why this fault has occurred, but the question is, next people ask what is the RUL, and that is what is known as fault prognostics. And to do fault prognostics, today the state of the art is people either used machine learning algorithm or from the physics of the problem we can develop model and used model based fault prediction, model based prediction. I am sure these models have to be accurate. Sometimes physics is not enough, or physics is not well understood, because the system is so complex that certain machine learning algorithms has to be used and so on. I will just give you an example. Think of a nuclear plant. Nobody would have waited for a nuclear plant to fail to actually see that what is going to happen and what is its or allow a defect to occur and predict and see what the remaining useful life is. These are all done through nicely developed software models of the plant, simulation models of the plant. So, in many systems, from the physics a good model is developed, and sometimes to supplement the model certain machine learning techniques like neural network, support vector machines are used, so that we have a robust model by which we can, looking at the past history of the defects in the machine, we can predict the future. I am sure everybody, if you visit a terminally ill patient in a hospital, everybody wonders and asks the doctor, what is the expected life of this patient and so on. Similarly, in a machine also, we try to use the past data obtained from sensors in this machine and see how we can find out the fault in the machine. So, certain definitions is what we need to know. So, fault diagnosis means detecting, isolating and identifying an impending or incipient failure condition, and the affected component subsystem is still operational even though at a degraded mode. Many times a defect has occurred that does not totally impair the machine, it will be still running, but then the fact that I have identified it is very, very important. And you will see a lot of this data analytics we are talking about, or signal feature extraction, help us find out the defect in the machine. Because let me tell you how CBM is going to happen or occur. See, suppose I have a machine with different components A, B, C, and if I capture the signal and do an analysis, it will so happen this maybe corresponds to frequency of A, frequency of B, frequency of C. So, if I take the signal, and of course, by the way this is a running machine. So, if I take this signal out of the transducer, put on this machine which has A, B, C components, the signal in the frequency domain certain amplitude will have a certain amplitude at these distinct frequencies. So, if A corresponds to the component A, B components to component B, C component F C corresponds to component C. So, every component in this machine has its characteristic signature or frequency in this spectrum. Like every human being has a characteristic signature every machine component also has a characteristic signature, and which we are trying to measure and relate. So, if component A has failed, maybe with time it is going to increase. So, this is what, and this will all be same. So, you see in this spectrum at different time instances, if I produce such spectrums, I will know that component A has failed. So, I would be able to detect that from such an analysis that component A in my machine has failed. I can take measures either to identify it or isolate it, or even get a component A replaced, because I have identified that the fault in this machine is because of a failure in component A. And imagine a large cement plant. For example, in a cement plant we have some critical components like a gearbox, like a kiln, etc. If you have understood that the motor, electrical motor in the cement plant has a critical is having a problem, we always can plan in advance and get this critical electrical motor stored in our inventory, because as soon as a defect has become severe, we can replace it. So, this would also save us time and so on. So, failure is different than fault diagnosis. Failure diagnosis is detecting, isolating and identifying a component that has ceased to operate, because a failure has occurred, and many a times as the condition monitoring consultants or experts, we are called when this has happened. Machine has failed, and then we are asked what was the reason why did the machine failed, and that is what we do, what is known as in failure analysis. We will cover about this in the later chapters, later lectures on failure analysis. Despite our best maintenance efforts, a failure has occurred. So, how do I find out the root cause of this failure? Root cause of failure, RCFA, root cause failure analysis. We need to find out. Fault, an abnormal operating condition is detected and reported. Today, the sensors are so smartly available that the machines itself, through the right data analytics, will indicate that a failure has occurred or what kind of corrections needs to be taken and so on. So, another definition is fault isolation. So, determining which component subsystem is failing or has failed. Now, fault identification, estimating the nature and extent of the fault. This is also sometimes important, because when you are talking about the RUL, this information is going to help us, well, how much into the till it fails we are into in the time domain. So, certain fault diagnosis techniques exist today, and the most popular being the data driven or the signal based, which I told you right in the beginning. We have a machine, put a transducer, get some signal, analyze it, see the characteristic frequency spectrum, and then try to correlate with the machine component. But many times I will be not allowed to get a signal from a failed machine. A nuclear reactor is a very good example. So, there we have to develop lot of models based on the physics of the problem, models sometimes so complicated that sometimes physics does not help us. So, we have to do some studies using techniques like neural network, etc., and I'll show you an example in the next class how neural network can be used to prognose the fault in a toolware. So, certain data driven fault classification, one is stored fault pattern library is in a fault classification. So, that means the characteristic defect signatures are already there. So, one can do a comparison. For example, when we talk about a machine, I have a shaft which is having a gear supported on a bearing, and there is a casing. There is a casing of the. So, this machine, there are three components. One is the shaft, other is the bearing, and gear. So, if I put a vibration transducer here, acquire some signal and I analyze it, some x t, see the failure in the bearing has a characteristic frequencies, failure in a gear has a characteristic frequency, failure in the shaft in the same in the terms of the shaft being misaligned, shaft being bent, shaft having a crack. So, all these have a definite pattern, and so in fact, today software are available which are very generic. You could be using it in any rotating machines. This machine could be a electrical motor, could be a gearbox, could be a pump, but the feature is the same. We have the shaft, bearings, gears, and so on. Another is looking at the feature vectors, and a lot of studies today are going on using neural networks, support vector machines, fuzzy logic, Bayesian networks, and so on to diagnose the fault. So, a lot of data driven techniques are being used to find out faults, and we will see how this can be done. But then in certain diagnostic methods, we also with time we can have certain bands. This is my usually this is my upper band. So, if a failure occurs, we put some upper bound. So, within this bound, if there is a failure, I need not get worried about. So, this could be changing, and there is a lower bound. So, with time, so this kind of bounds are also there in the software. There are many data driven diagnostic methods from statistical correlation regression methods, fuzzy logic, neural network, and so on. But there are also many physical model based methods. I will just give you one example of if a crack has occurred in a component like the shell of a rotary kiln, casing of a gearbox, and which is subjected to fatigue loading. This is the load cycle. So, this the crack propagation, the crack depth depends on certain material properties, and these powers are there. So, this is the famous Paris equation. There is a time taken for the crack to grow. So, we can use such models to estimate that after what time the crack would have come to a level which is not possible to be managed. And then of course, today a lot of numerical techniques like finite element analysis are being used for model based diagnostics, and that can be used to find out the faults in any structure which has a crack. But such physical model based, I was just giving the case of a crack. Today for rotordynamics, a lot of work people are doing on model based techniques for finding out faults in rotor bearing systems, using the technique of finite element method to model the system, and of course, update the models with realistic experimental data and so on. So, once robust models are available, it is very easy to prognose the fault. So, prognosis is the ability to predict accurately and precisely the remaining useful life of a failed component. See, if I have a model, I can always use that model to do what is known as the forecasting. So, prognostics is nothing but what is known as the fault forecast. To determine REL. And models will help us, or even sometimes doing an filtering, we can have an adaptive filter which will let you know also looking at the past history. So, more resources on this can be found in my book, and you can contact me over email or my phone. Thank you.